So today, let me give you a few examples of how things work and some applications of cohomology, and then we'll go back to these advanced techniques, and I will show how things actually pack nicely in another black box of derived categories. So let me start with two versions of Riemann-Roch theorems. So the first one will be for curves, and the second one will be for surfaces. And then there is the general formulation of Grothendieck Riemann-Roch that I don't want to give now, but if you understand, because it requires some chow groups. But in general, let's observe that we can now define a very simple characteristic. This characteristic is chi of any quasi-coherent sheaf. So for any quasi-coherent sheaf E, we can take the alternating sum of the dimensions of hi on x on E. And here, say, I assume that x is projective and E is coherent. You can think of a locally free sheaf. This is what we're mostly interested in. So this is a map from where to where? Well, this is a map. The right-hand side belongs to Z. But actually, you can always form quite a funny group. So this is an observation. Namely, to the category of coherent sheaves on X, you can associate, let's say smooth. For simplicity, but there will be a little bit of a difference of how you define. I will say smooth coherent sheaves on X. You can associate an abelian group called the Grothendieck group, K naught of X. And the generators are isomorphism classes. So these are isomorphism classes of, well, vector bundles. But in this case, you can look for coherent sheaves. And the distinction, this is where the distinction between smooth and non-smooth is, because if you say vector bundles on smooth and coherent sheaves, you'll get the same thing. In general, you won't get. Let's say coherent sheaves. So this will be mostly our important thing. These are the generators, and the relations will be given by short exact sequences. If you have a short exact sequence of coherent sheaves, then to this you impose a relation that the class of the extension of E equals the class of E prime plus E double prime. So what is this? This is a group which defines the universal additive invariant on vector bundles or coherent sheaves on X. So for instance, you immediately see that this map chi, technically, we defined it for all coherent sheaves, but it naturally extends to a map from K naught of X into Z. And namely, what is an element in here? This is a sum of some generators, N, E, the class of E. And the coefficients may be negative, for instance, but this is sent to the sum of N, E, chi of E. And what are we using here? We're using the fact that to a short exact sequence of coherent sheaves or vector bundles, you have an associated long exact sequence of cohomology. So check, the only thing you need to check here is that chi of E does not depend, first of all, on the isomorphism class, but also chi of E equals chi of E prime plus chi of E double prime for any short exact sequence, and this comes from long exact sequence of cohomology. So this is our first kind of ingredient, and the second ingredient comes from. So let's rewrite it properly. Say if x is of dimension d, then we know that cohomology of degrees higher than the dimension vanishes. So for instance, chi of e equals, well, I introduced the notation last time, h naught of e minus h1 of e plus h2 of e minus etc. So for curves, what we get is chi of e equals simply h naught of e, which is the global sections, minus this first cohomology. All right, so for surfaces here, we'll use it. We have three terms. All right, well, now the second ingredient that I want to recall is third duality. And in its simplest form, it says specifically that if E is a vector bundle, then let me write this way. Well, hi on x of E is isomorphic to the dual of h d minus I on x of E dual tensor omega x, where this omega x is, well, it's nothing but the top wedge power, the determinant of the cotangent bundle. This is a line bundle, 1, which is the same as omega d. All right, so this is the dual space. So for instance, what we get is we get immediately the corollary from here is that hi of E equals h d minus I of E dual tensor omega x. So we twist our vector bundle by, we first take the dual and then we twist by a certain line bundle and we get equivalence of numbers. So what we immediately see is that, say, for curves, we can rewrite chi of E as h naught of E minus h1 of E. But h1 of E, this is the same as h naught of E minus h naught again of E dual tensor omega c. And similarly, you can also rewrite it another way as h1 of E dual tensor omega x minus h naught of E dual tensor omega, well, c, sorry, root x here. This is c. All right, and the last term is what? It's just minus chi of E dual tensor omega c. So in general, what you always get on any variety, so surfaces, you get chi of E is actually equal. You just look at the alternating signs. It equals chi of E dual tensor omega c. And for any d, you get chi of E equals -1 to the power d chi of E star tensor omega c. So let's return to our original problem. Most of the times you want to compute global sections of stuff. So let's see, on curves, you want to compute global sections of a certain vector bundle. And it turns out that it's very easy to compute this chi. And then by reasoning about h1, you can try to reason about the global sections of your bundle. So on curves, it's done the following way. And this is the Riemann-Roch for curves. Now we can state it. And the first version, let me recall that if L, so x equals c, is a smooth projective curve, then any line bundle L, so the group of isomorphism classes of line bundles, usually called the Picard group, any line bundle is isomorphic to the bundle associated to a divisor D, where D is the sum of certain finite number of points with coefficients, and then the degree of L, there is this homomorphism from the Picard group to Z. The degree of L is defined to be the sum of Ni, and let me remind you from, say, complex analysis or algebraic geometry, from what you know, this line bundle L always have a meromorphic section or a rational section, where this sum of Ni and Pi is the sum of zeros and poles. So Pi's are zeros or poles, and Ni's are multiplicities of those zeros and poles. Okay, so the last thing that we need, well, we don't need anything else. The Riemann-Roch formula for curves says specifically that chi of L equals the degree of L, and the degree is usually a very computable invariant, plus chi of O, the structure sheaf, and then chi of the structure sheaf we can rewrite. We've spoken about it. Chi of the structure sheaf of C is H naught of O. This is the global sections, but we have a projective variety, smooth projective connected curve, irreducible, or at least connected is fine. Yes. So then if it's smooth connected, then it's irreducible. You have only constant global sections. The only global functions are constants. So this dimension is 1 minus H1 of O. And this number we call G, and this is the genus. So as I indicated last time, this genus is literally, in case you consider everything over C, and this is your curve that is defined as a complex Riemann surface, then G will be the number of holes given by the topological type. This is a certain statement, but it's not hard to prove. Not the main part of our course. So this is specifically genus. So first of all, how can we derive this formula? Well, it's very easy to derive this formula. Namely, we can do it by induction on degree or some kind of part of the degree. So it's the induction on the sum of the moduli of Ni. And the base case is just when L is isomorphic to the structure sheaf. Then the formula just says that chi of O equals 0, which is the degree of the trivial line bundle, plus chi of O. So there's literally nothing else to prove. And now the inductive step. The inductive step is also very easy. Namely, I want to decrease this number Ni, the sum of the absolute values of Ni's. But remark that if I take the following short exact sequence, if I consider the sequence O of minus P goes to O, goes to and then what is in the quotient? In the quotient, we have the structure sheaf of the point, simply. Then from additivity, of chi, we get that chi of O minus P equals chi of O minus chi of O of P. But chi of O of P, it's very easy to compute. This is 1. So it all equals -1 plus chi of O. And this is specifically the degree of O of minus P, because just the ideal sheaf of your point. More generally, if L is arbitrary, you can just tensor the star by L. And what you get is you get the line bundle L of minus P goes to L. And what do you have here? Well, it's again just simply the structure sheaf of your point. It doesn't feel the line bundle structure outside. And then the same argument specifically says that chi blah, 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 just repeat it. And this is the derivation of the formula. Well, the formula is incredibly powerful because already you can deduce many, many things about it if you use Serre duality as well. So some immediate corollaries. Well, first, you can compute the degree of omega of the sheaf of differentials. And in theory, let me remind you that the genus is a certain computable thing. For instance, we've discussed that if you have a plane curve given by a degree d polynomial homogeneous in two variables, then the genus is 1/2 of d minus 1 times d minus 2. So how do we compute this degree? Well, remark that chi of omega c equals the degree of omega c plus chi of O. But on the other hand, we know that chi of omega c is minus chi of O dual, which is minus chi of O. So from this, we deduce that the degree of omega c is minus twice chi of O, which is 2g minus 2, because chi of O is 1 minus g. So we already have this. And then from the next step, with this, here's a very simple observation. Remark that if the degree of L is less than 0, then H naught of L equals 0. So why is that? Well, again, if you have a global section, if S is a global section of L, then from the construction of line bundles from Cartier divisors, you deduce that L is the O of the sum Ni Pi, where Pi are zeros. And for instance, all Ni's are greater or equal than 0. All right, this is good. So thus, if, and here is an important part, H naught, sorry, if L dual tensor omega c has negative degree, then H naught of L dual tensor omega c equals 0. But one version of our formula says specifically that H naught, I'm just rewriting chi, H naught of L minus H naught of L dual tensor omega c equals the degree of L plus 1 minus g, where this is, by third duality, h1 of L. So in particular, we conclude that if the degree of L dual tensor omega c is less than 0, then h1 of L equals 0, and then h naught of L equals simply the degree of L plus 1 minus g. And usually the degree and the genus are very, very computable. What is this? The degree is additive. So this is minus the degree of L plus the degree of omega c. But we've computed the degree of omega c. So this thing is less than 0 if and only if the degree of L is greater than the degree of omega c, which equals 2g minus 2. All right, so for line bundles of high degree, you can immediately compute global sections just simply by using this Riemann-Roch formula and seeing that it works. So how does it generalize to vector bundles? So this thing easily generalizes to vector bundles, not just from line bundles. And specifically, I claim that chi of E now equals the degree of E plus rank of E times chi of O. Why is this so? Well, first of all, what is the degree of E? The degree of E is just the degree of the line bundle determinant of E, which is the same as the top wedge power of your line bundle. Well, rank is rank, of course, say rank 2 or rank 3 or whatever. And now from this, how do you derive this formula? Well, you quite easily derive this formula because actually you remark that both sides are additive with respect to short exact sequences. Indeed, what do we have here? I've said that chi is additive because it comes from k naught, from the universal kind of additive invariant. Degree is additive because if you have a short exact sequence, that the degree of the middle term is isomorphic, well, is the sum of the degrees of the side terms, literally because the determinant of the middle term is isomorphic to the product of the determinants. Finally, this guy, rank, is also additive in short exact sequences of vector bundles. But now any vector bundle can be realized as an extension of a line bundle and the quotient vector bundle. So this is a good exercise. It follows from everything we've discussed so far, by the way, from some theorems, where this is rank 1 and this is rank E minus 1. That's it. So this is how you reduce to the case of rank 1, but rank 1 we've already covered. So you have this beautiful formula. So far it seems very benign, but it has immediate, very nice corollaries. Namely, you can consider moduli of vector bundles on C, and then you need to fix some parameters, say of rank equal to R and the degree equal to D. Okay, we've fixed these parameters, and then it turns out that there are various types of constructions, both in differential, coming from the analytic side, from the algebraic side. You can construct a certain variety, or stack or whatever, but most parts of the variety of nice enough vector bundles on your curve with these fixed parameters. And this comes up everywhere, especially in theoretical physics these days. Well, even before we construct this thing, we can actually do something very nice. We can compute its dimension without knowing. So we know how to compute its dimension from deformation theory. Namely, I claim that you have a certain isomorphism class of vector bundle, which is a point in the moduli space or stack on C with this R and D parameters. Then the tangent space and you can compute this tangent space by knowing, recall from algebraic geometry from the beginning, that the tangent space can be computed as morphisms from dual numbers into your scheme. But if you think long enough of what does it mean to construct a morphism from dual numbers into its scheme, you will actually realize that it's the same as constructing an extension. So this will be isomorphic to x1, for which we discussed last time, of E together with E. But now this is x1. On the left-hand side, I have a locally free sheaf, a vector bundle. So we know that this is actually isomorphic on its side to simply global sections H naught on C of the bundle E dual tensor E. Sorry, H1, of course. What am I saying? H1. So let's see what Riemann-Roch tells us. Riemann-Roch says that chi of E dual tensor E is the same thing as H naught of E dual tensor E minus H1 of C E dual tensor E. And now this is specifically the dimension of the space that we're looking at. Where do we move from here? From here, we know, first of all, so this is the dimension of the tangent space at E. And this equals the degree of E dual tensor E. But the degree of E dual tensor E is, as you might guess, is 0. It's twice the degree of E dual plus twice the degree of E, sorry, R times the degree of E dual. You just see how the degree works well, let me write it this way. So it's R times the degree of E plus R times the degree of E dual. And of course, the two cancel. Plus R squared, this is the rank of E dual tensor E, times chi of O. So what do we get in the result? The dimension at E to our tangent space is equal to R squared times G minus 1, this is minus chi of O, plus, well, H naught of E dual tensor E. Now, if E is nice enough, so say if it's what's called stable, then this dimension H naught of C from E dual tensor E, recall that it's nothing but isomorphic to simply Homs from E to itself, and this is one-dimensional. So for instance, this dimension is 1, and of course there are always stable bundles, and you conclude that the dimension of the moduli space on C of rank R bundles and degree D does not depend on D. It equals R squared times g minus 1 plus 1. Because the dimension is, of course, you can compute it at the generic point. So remark that we have not used any hardcore things or anything, but we essentially used a lot of things that come from cohomology, and even for curves, it gives quite important, quite interesting results. So this is maybe the derivation on this thing is the first very nice application that you can get. Maybe let me say a few words about surfaces now. So second, surfaces. So on surfaces, we can try and compute. Well, we want to have some sort of a similar formula. But the first thing that I want to introduce is I want to introduce intersection form on, again, the Picard group of X, where X is a smooth projective irreducible surface. And now on Picard group on X, of course, if we have a line bundle, then it's O of the form O of the sum Ni Ci, where now Ci are curves on S. All right, well, as you might guess, there is one part of, there is a certain type of intersection form, namely if C and C prime intersect transversely, then we can compute the intersection number as just the number of points of intersection. So in particular, in this case, you want the pairing of O of C and O of C prime to be simply C dot C prime. In this case, we want this in such a case. All right, well, it turns out that you can define the intersection purely homologically, and you just simply put that the intersection of L and will be a mess of notation. Well, let me still write L prime. You put it as chi of O minus chi of L. Well, usually you write to the power -1 to denote the dual line bundle, because Picard is a multiplicative group written multiplicatively, minus chi of L prime inverse, and finally plus chi of L inverse tensor L prime inverse. So this is a kind of inclusion-exclusion formula on line bundles given here. You start with the empty product, you subtract all one term, negative products, you add this product. So here's a very good exercise using the exact sequence. And here's the sequence. 0 goes to O S of minus C prime, goes to OS C minus C plus OS minus C prime, goes to OS, goes to O of the intersection of the two curves, deduce, let me introduce some notation, something like 1. So deduce 1 from 2. So for instance, 2 satisfies the properties that we want. So moreover, one can check. Again, this is an exercise that chi, well, sorry, not this chi, that this product is a symmetric bilinear form going from the Picard group of your surface to, well, again, Z. All right, why do we need this product? Well, this product can be computed, first of all, most of the times, but here is something more interesting that you can deduce. Now we can write what the Riemann-Roch formula specifically says. So the Riemann-Roch for surfaces. So let L be a line bundle, an element of the Picard group of S. Then I claim that chi of L, and the first part is always similar, of course, it equals to chi of S, of O of S, sorry. And then this is something, an interesting term, you get 1/2 of L, and then you pair L with, well, let me write it this way. L comma L minus L comma omega S, where omega S is as usual, sorry, where this is as usual determinant of omega S. So it's top differential forms, the locally free sheaf, the line bundle of top differential forms. And now again, a lot of the times, what you actually do is you do something very simple. You specifically use the definition of this intersection by choosing appropriate representations of your line bundles. You use this to literally compute the intersection of the corresponding curves that define your divisor. And similarly, well, it's a little bit harder for this part, but again, using some sort of moving lemma, you choose appropriate sections and you compute these wonderful intersections. So a very good exercise is to literally check this for line bundles on P2. Exercise, check this formula for line bundles on P2. And recall that each line bundle, the Picard group on P2 is isomorphic to Z, and every line bundle is of the form of an H, where H is a line, a hyperplane, well, a line in P2. All right, so this is a nice enough formula for the intersections. Here's the derivation of the formula. And again, the whole machinery gives you a very easy and nice answer. So let's compute the intersection product. The following intersection product. Let's compute the product of L inverse with L tensor omega S inverse. Just using our exact definition. So this thing equals chi of O. This is the term we're interested in. Sorry, this is the term that appears in the formula, minus chi of the first argument inverse, but we already took L, so it's L inverse. What we get is chi of L minus chi of L inverse tensor omega S plus, and then we should multiply these two and take the negative, chi of omega S. All right, Well, the thing that we have here on the right, remark that this is by Serre duality chi of L, and this by Serre duality is chi of O. So on the right-hand side, we get twice chi of O minus chi of L. And now that's it. You need to just open the brackets, remark that this thing by bilinearity, the thing that is written in the front when moved to the other side is exactly what we want. So we get that chi of L is indeed chi of O plus 1/2 of L comma L tensor omega S inverse. And now by bilinearity, this is the same as the thing that we started with. All right. So here's this is one typical application of this thing. And then of course, so how you usually very often this is used to give a lower bound. So namely, you can always rewrite chi of L as H naught of L minus H1 of L plus, and remark that this greater or equal than 0, and here you can write H2 of L, but H2 of L is the same as H naught of L inverse tensor omega S, and this equals 1/2 of blah. And now you see that you get an inequality H naught of L plus H naught of L inverse tensor omega S is greater or equal than something. And from this, you can derive that either you have global sections of your line bundle or you have global sections of the inverse of your line bundle tensor omega. So this is a very typical trick when you start studying surfaces, and a lot can be derived from this. Okay, so this was our kind of excursion into Riemann-Roch theorems. So next step, which we do not, next step that we do not discuss is the Grothendieck Riemann-Roch, and this is the big generalization to, well, a big generalization to arbitrary dimension, for instance. Okay, so back to our tools. To our tools. And so far what we've seen, for instance, cohomology, which is which are the derived functors Ri of the global sections functor. And these, as we've seen, can often be computed using resolutions. Say sometimes you choose an appropriate resolution, and if you choose a resolution by acyclic objects, then you can compute this via, it's technically a degenerate spectral sequence, but this is what you do. Also, what we had is derived push-forward functors, and again, these are kind of defined using, well, I said it can be defined using two ways, but in a way it kind of can be computed. Using resolutions. There is more to that. There are more operations. If you want all kinds of additivity, then actually you can define appropriate tensor product. So remark that tensor product is exact when applied to vector bundles, but only right exact in general. So what you can do is you can define the so-called derived tensor product, or you define shiftor. So instead, for say coherent sheaves on smooth projective varieties, define tor I between E and F by choosing a resolution by vector bundles of any of the arguments, say V0, V1, V2, etc. And then putting tor I of E, comma F to be the cohomology of the complex. So this is cohomology. I will write it this way, H, the homology, because the indexing, the HI of the complex V tensor F, where this is the usual homology of the complex. And finally, if you think how the pullback is defined in algebraic geometry, well, first you take F inverse topologically, and this is an exact functor. But next, you take the tensor product over F inverse of the base of y with O of x. So you immediately see that the pullback is again right exact, but not exact in general, though it is exact on locally free sheaves. And again, you can define the left derived functor Li f upper star of E by again choosing a locally free resolution and specifically saying that it's Hi of f upper star applied to V. So you see that there are plenty of these constructions that kind of I'm skipping most of the details, but in a way they specifically say that you can define various things using various kinds of resolutions, and then if the resolution is good enough, then the result does not depend on this choice, and if the result does not depend on the choice, well, then it's well defined, and then you often have some kind of spectral sequences or something. So the solution to this whole, so to this mess or zoo of definitions is derived categories. So what are these derived categories? Well, derived categories are actually very, very easy to understand if you start with commutative algebra. Part 3, derived categories. So let's start with a commutative ring. And we want to think about the category, say, Noetherian, everything very nice. I mean, you don't need Noetherian, I just want to explain how it goes. And let's say that M is a module over A. Well, we've been taught for a long time that to study modules over a ring, the last thing you need to do is the same as in linear algebra. In linear algebra, the biggest sin you can commit is choose a basis. I mean, if you're choosing a basis, either you're doing something wrong or you're actually solving a problem that is at the end of your path. I mean, at some point you need to do some computation, but the longer you defer making any computations, the better it is. However, let's weirdly return to the very idea of choosing a basis. So instead of thinking of a module as some kind of abelian group, together with the action of your ring, I specifically want to choose generators and relations. So what does it mean that I choose a set of generators? It means that I choose a surjection from a certain collection, from a certain free module of A into M. So this is what it means to pick generators. I mean, the corresponding, you pick some elements that generate the whole module, and you send the corresponding basis element of your free module into this element, to the corresponding element of your basis. However, in linear algebra, you can always find such an isomorphism. When you're doing commutative algebra, you don't. So you have some relations. There is a certain kernel here, which probably should be denoted by R1. And this is your submodule of relations. Well, when you're presenting your modules as generators and relations, you pick some equations, well, some expressions that vanish. And again, when you pick such expressions, when you write them down, what you're actually doing is you're choosing generators for your module of relations. So you get a further map. But this can have further relations. There can be relations between your relations. And this is the kernel of the corresponding map there. So it's kind of this is the kernel of this, and this is the kernel of this map. All right, well, I just continue the process. I say that I choose a surjection here. And in the end, what I've just done is I've represented my M as a complex. So this, so these two should be interchangeable in a certain way. I should not have any distinction between the module and the presentation by relations and generators. But we all know that even in commutative algebra, you can choose plenty of bases. So to which extent this presentation is non-unique? Well, again, if you do a little bit of homological algebra, then you will find out the following two things. So the main result is if you have a morphism and two resolutions, so say F0, F1, etc., G0, G1, etc., then any F has a lift to a morphism from F to G, and it is unique up to homotopy of morphisms of complexes. All right, has a unique lift. The one thing that you do is also, if you want to have a nice enough category, maybe allow resolutions to be projective. So far you don't need it. I mean, you can literally do this free one. All right, so what do you actually get? You have this category of resolutions over A. And what is this category? This is category where the objects are complexes of the form P3, P2, P1, P0, 0, with cohomology, with homology 0, 0, 0, question mark. So the last map may not be surjective. It's a complex. It's exact on the left, and then 0, 0, obviously. What are the morphisms? The morphisms are morphisms of complexes modular homotopy. So homotopic maps homotopic to 0 form what's called an ideal in this category. So if you have two maps that are, the difference is homotopic to 0, then if you precompose or postcompose with anything, they'll still be homotopic. And you get a functor from here, which is just taking 0th cohomology, H0, to A mod. And the previous statements say that this is an equivalence of categories. All right. So if you do enough homological algebra, you will soon realize, so far it doesn't give anything interesting. It says that you have modules and then you have some sort of weird category of resolutions, and it more or less gives you the foundations for explaining why certain, say, derived functors, classical derived functors, are defined the way they are defined. All right. So what is the idea of the derived categories? Idea. Relax restrictions imposed on the category of resolutions. How do I relax these restrictions? I just simply consider resolutions P such that, well, first Pn equals 0 for n very, very big enough. And then there are various versions, but say for our applications, let's say that Hi of P equals 0 for the absolute value of I big enough. So in other words, you have finitely many cohomology of these complexes. And also, if you go far enough to the right, that you will only get 0. So what is good about this category is that, so morphisms as before. on the category, so specifically objects. Then this category is closed under various operations. So first of all, it's closed under the shift operation, where if you shift a module by t, you just renumber, I, then it's p of I plus t. So there's this very common shift operation. And, and what is called, wait a second, taking cones. The bad news, this category is not abelian anymore. Good news, using this, it is easy, very easy, to define our so-called derived functors. And moreover, some formulas which were spectral sequences before become much nicer. All right, let's make a 7-minute break, please. And then we will start with the proper definition of derived categories and the construction of various stuff in there. All right? All right, so the fascinating idea of Grothendieck and Verdier, implemented by Verdier mainly. So Grothendieck plus Verdier. They say specifically that what we do is we define a category, well, the derived category of X. So for simplicity, X is smooth projective. We define D of X to be the category where objects, well, let me first do it in a proper way. We start, in order to define D of X, we start with C of X to be the category of all possible complexes of coherent sheaves with finitely many non-zero terms. So just a complex composition of two consecutive maps is zero. And we think of these as the category of resolutions, if you wish. Inside, there are different kinds of resolutions. Say a coherent sheaf can always be substituted by its resolution by vector bundles. And if your variety is smooth, then this resolution will be finite. Okay, and now what you do, so what is the morphisms are just simply morphisms of complexes. Then you put the derived category to be C of X, and this is what's usually denoted by this. So we formally invert all quasi-isomorphisms. And I recall that if you have one complex X, a morphism between complexes, and a morphism to a complex Y, then to this you get a corresponding morphism HIF, which goes from, well, let me stick to my notation, HI of X into HI of Y. And F is called a quasi-isomorphism if all HIF are isomorphisms. So in other words, quasi-isomorphisms are morphisms that induce isomorphism on cohomology. All right. So how do you formally invert quasi-isomorphisms? Well, if you think about it one way, so a morphism in d of x is something like a diagram of the following form. You first replace x by a quasi-isomorphic complex that maps into your x, then it maps to y1. Let me redenote it by 1. Then you replace y1 by a quasi-isomorphic complex, and then you map to etc. up to you replace by a quasi-isomorphic, but you see you're going in the opposite direction. You kind of formally add in here. And then, I mean, it's very easy to compose this way, but up to some equivalence. And if you want to do it properly, when you start reading about the literature, actually you can do this localization in 2 steps. You first observe that homotopic morphisms give isomorphic maps, well, identical actually maps on all HIs. Thus, if you want to invert it in some universal way, you can first pass from C of X to the homotopy category, so-called, and this is where the objects are complexes and morphisms are morphisms of complexes up to homotopy. This is homotopy. And then it turns out that it's very easy to, well, it's much easier to construct the localization of this up to quasi-isomorphisms. And this is due to something which is called, so this guy has Ore conditions. I do not have time to explain everything about the Ore conditions, but basically, if you think a little bit about how you construct, this comes from non-commutative algebra. If you want to localize a non-commutative ring in a multiplicative system, then you must request, well, one of the ways to do it easily is to require some conditions. So the conditions are usually something like, okay, let me write down one condition. One condition is that you want to be able to replace a commutative diagram of this form, where this is a quasi-isomorphism. You want to be able to replace it by a commutative diagram where this is an actual morphism into some G, and then a quasi-isomorphism going from Y. So you need to be able to switch between kind of these kind of terms. And if you are able to do this plus some more properties, then it's actually quite easy to define an equivalence relation, and every morphism will be represented this time by a diagram of this form. You literally replace X with something which is quasi-isomorphic going into it, and then isomorphism in the other direction. All right. So this is all so far very abstract. However, remark that at least d of x remembers all the hi's of complexes. Right? Because when we inverted quasi-isomorphisms induce isomorphisms on cohomology of complexes. So for instance, somewhere in there lives the category of resolutions, and also it comes with a functor from coherent sheaves on X, which goes into d of x. And the functor sends E to a complex which has E concentrated in just 1 degree. However, this time, this single sheaf or this single vector bundle becomes isomorphic to all kinds of resolutions that it has. So this is what's fascinating about these derived categories, and this is why they were originally invented and introduced. They were introduced for the following reason: all our functors extend to functors in defined on derived categories. So let's start with global sections. So instead of global sections, you have to add derived everywhere. So from d of x, you have a functor, which is called the R gamma, which goes to the derived category of K vector spaces. So this will be just, again, complexes of vector spaces, finite, and all quasi-isomorphisms reversed. And if you think about it for a little bit, this is isomorphic to just graded vector spaces, graded K vector spaces. So there is a certain functor that is defined this way, and the property of this functor is that if you look at R gamma, apply it to E, and then take ith cohomology, or the same as the graded piece, it will be simply hi of x on E. So this is the kind of first thing that you have. The next thing that you have is if you have a morphism, if you have two guys, now you have morphism from d of x times d of x into d of x, and you have something that we still call the tensor product functor, but now it has the following property. Let's call it, usually people put an L in here. It has the property that if I have two sheaves, if I take this derived tensor product, now it's a complex. It's an equivalence class of complexes, if you wish, on X. But if I take H minus I of this complex, minus because I'm switching from homological to cohomological notation, just as a complex, then this guy now belongs to coherent sheaves on X, and this will be the same as Tor I of EF. Same for hom. You get a functor from d of x times d of x, which goes to d of, say K vector spaces, which is called R hom. And the property is HI, believe it or not, if you plug in just two vector bundles or sheaves, then this is the same as xi from E to F. So this is what can be done on one scheme. So far we have tensor, Hom, global sections. You have more if you have a morphism of smooth projective varieties from F to Y. Then there is a functor RF lower star, which goes from d of x to d of y. And the property is, as usual, if you have a locally free sheaf or a coherent sheaf, then HI RF lower star of E is now a complex, well, an isomorphism class of complexes on Y, but if you take the cohomology of this complex, then it will be RIF lower star on E, the way we defined it before. What did we have else? We also have the left-derived functor of F upper star going from d of y into d of x and blah, blah, blah. So usually exactly as previously, these guys are defined the same way. So what is the beauty of this thing? Well, first, we can now define things for complexes and not only sheaves. And interestingly enough, it gives you often quite a lot of information, but let's kind of postpone it for a second, maybe. Here's a more important thing. It's like there's simple functoriality. Since things are defined using universal properties, these functors are defined using some certain universal properties. You can look it up afterwards. But the most important thing to remember is now if you have a couple of morphisms x to y to an arbitrary z, say, then from general principles, you derive that the derived functor of the composition push forward is isomorphic to the composition of the derived functors. And now, using very standard techniques as before, you produce immediately spectral sequences. Which spectral sequences I will write in a second, but the spectral sequence approach is, the spectral sequence corollary is maybe not very interesting. What is more interesting is you can have now, so before we only had a spectral sequence for, well, say for the composition of gamma composed with F lower star, but this is the same as two maps. So now this in very short terms, you can here arbitrarily many maps involved. So you get various spectral sequences. What is the first spectral sequence that you get? Well, the first spectral sequence that you get, if G is a morphism from Y to the point, which is spec K, then actually G lower star is gamma, is just the global sections functor. And we get the usual spectral sequence that whose second page EPQ is HP of Y of R QF lower star of E, and then it converges to HP plus Q on X of E, except E can now be a complex. More importantly, for just the general machinery, we don't have to reprove things every time by choosing appropriate resolutions. It says that you have even more spectral sequences. So if G is arbitrary, you get a spectral sequence now. G is arbitrary, which says that now this is in terms of sheaves, RP, G, lower star, applied to R, Q, F, lower star of E, where E is now again maybe a complex. This converges to RP plus Q, F composed with G, lower star E. Even more interesting, if you take F to be the identity functor, now F to be the identity map, you get another spectral sequence for absolute free. If you take the identity map, the spectral sequence, you get EPQ to be the corresponding term is RP G star, and then the derived functors of the identity map, the derived functors, are just cohomology of the corresponding sheaf, RQ of E. Of the complex, sorry, no, the cohomology of the complex. And this converges to RP plus Q of E again. So G lower star of E. And finally, if F equals the identity and G is a map from Y to spec of K to the point, spec of K, you get an absolutely wonderful spectral sequence, which explains in a way how you find cohomology for complexes. And this spectral sequence is EPQ2, which is HP. So the usual cohomology of the cohomology sheaf HQ of F which converges to HP plus Q on X of F. I'm switching from E to F, where this is defined as RP plus Q gamma. So this is defined already purely for complexes. So this is one bunch of formulas that is very, very nice. Well, we have some other formulas, but let me also note that one can define duality on D of X. So before we could associate to a vector bundle its dual, but now we can associate to a complex its dual. And again, the idea is that it's just a way of packing down nice information. So here, think of F as of a locally free resolution of a quasi-coherent sheaf, well, of a coherent sheaf. And then say if you want to take the dual of something, so then dualize term-wise. What I'm trying to say here is that you can try to define a dual for a coherent sheaf by first taking a locally free resolution, replacing your sheaf with the locally free resolution, and then to each term of the resolution, you simply apply the dual. This just says that you can do this in a very, very, well, in a very generic way. So all kinds of formulas work. Let me just use one more very important formula. That is very often used is the so-called projection formula. So if you have vector bundles, then you can, or now any arbitrary things, then you can actually consider the following thing. So I have a morphism here. Assume I have E, which is in D of X, but each time think that E is an actual vector bundle and F is in D of Y. Then I can compare two things. And one thing is I can take the derived pullback of F. I can take the derived tensor product with E, and thus I get a bundle on X. And then I can take the derived push forward, and I get a bundle of Y. But instead, I could have just taken the tensor product derived of F with the derived push forward of E. And it turns out that if everything is smooth, at least, then here you have an isomorphism. And again, derived push forwards are what? They are giving you higher derived push forwards. So if you pass to cohomology, you will get certain spectral sequences as before. But most importantly, if you have a difficult enough diagram, then in the very end, you will get, well, you will get a certain big result. Okay, finally, let me give you one more very important statement, and this statement is the kind of big version of Serre duality. So let me write it here. I mean, there are many of those, but one way of doing it, if you have a morphism from X to Y, say a smooth morphism again, then you can define omega F as the determinant of the relative sheaf of differentials. And technically, what is the relative sheaf of differentials? Well, you have an exact sequence of differential forms on X, pullback of differential forms from Y, and then the quotient of one by another is the relative one. So put it as omega X tensor F upper star omega Y inverse. So you want to quotient, thus you take the inverse here. All right. So the big version of this Serre duality says specifically that the derived push forward, and then something I haven't said specifically, but you can also define what the sheafified Hom is. I'll say in a second. Between F and LF upper star E. These will be complexes, tensor omega F, and then shifted further by the relative dimension of F, where the dimension of F equals the dimension of X minus the dimension of Y. This is isomorphic to R Hom between R F lower star F, comma E. So here is an X. First of all, what are these R Homs here? Again, we have a functor Hom which is the sheafified Hom from coherent sheaves on X times coherent sheaves on X to coherent sheaves of X, the sheafified Hom. So on any open subset, you consider Homs between restrictions on the corresponding thing. You can do this, blah blah blah. But actually, what this thing says there? So here are two exercises. First, derive Serre duality from this, the usual one. And the second observation is that you can look at the following functor. You have a functor from d of y into d of x, which sends any complex, sorry. But again, forget about complexes. You can think about sheaves. Thinking about sheaves is already good enough. To the derived pullback of E, and then taking the tensor product, and here I just take the usual one. In general, you need to have the derived one, but since everything is smooth, everything works nicely, plus this shift thing, which just shifts the complex, the degrees of the complex. So let me denote this functor by F upper Schrick. And now the most important thing that I did not explain is that usually, say topology, or algebraic geometry or whatever, you have an adjunction. Namely, you have Hom between F upper star of X, Y is isomorphic functorially to Homs from X to F lower star of Y. Well, X and Y are bad. I'll put tildes here. This is less bad. So you have the same thing for direct functors. And the thing is specifically LF upper star, sorry. I'm not used to writing, usually people drop this, is left adjoint to RF lower star. So what does Serre duality tell us? Serre duality a la Grothendieck it says specifically that RF lower star is left adjoint, so we can construct the right adjoint to it, which is F upper Schrick. The whole thing about derived categories started with the following observation. If you want Serre duality for more general spaces, more general morphisms, say something suddenly becomes not smooth. Something is for more general morphisms. Then actually F upper Schrick, this functor, is defined only on the level of derived categories. So there are two statements packed in there. The first statement is that Serre duality itself is a statement about a certain adjoint functor. And if you look at it in the way I wrote it here, so this is looking at this formula, then actually you'll recognize, probably by passing to some global sections or whatever, that this is specifically the definition. This is what adjointness means. So now here, what you get is you specifically get that Serre duality is a statement about existence of a certain adjoint functor and its form. And this adjoint functor does exist in very big generality, but in general, you cannot define it using only coherent sheaves. This is the most fascinating kind of corollary of this whole business. All right, well, so this is where it all started from in the last remaining minutes. Let me make a few comments. So for many years, these derived categories remained just black boxes. And by remain black boxes, it means that, well, you can use this thing to define various functors. Then actually, when you write your paper, instead of writing 50 very complicated spectral sequences, you write a very nice diagram. You use things like the projection formula and some base changes and the composition of functors instead of spectral sequences of derived functors. And eventually, you arrive to some point where you can actually do a computation. And this time, all the details kind of have been kept for you. You do this computation, you get a result, you're very happy. I mean, but essentially, it's a way to manage all the complexity of the information about higher derived images, etc., etc., etc. But the categories themselves were imagined to be very, very complicated. But then happened something very, very interesting. And this is a theorem by Beilinson. And in its simplest form, let me state it this way. Okay. Let me state it in the following form. The derived category of coherent sheaves on a projective space Pn can be very easily described for instance. It is actually equivalent to the derived category of the endomorphism algebra of the following bundle of the sum of O of I, where I ranges from 0 to n. So this is a finite dimensional algebra. Here's an example. The derived category of P1 is equivalent to the derived category of the endomorphism algebra of O plus O of 1. And what is this endomorphism algebra from O plus O of 1? Well, it can be written as the path algebra of the following quiver. Let's look at the morphisms. You have one-dimensional morphisms from O to itself. There is no derived anything anywhere here. Just simply one-dimensional from O to O, one-dimensional from O to O of 1. There are no maps from O of 1 to O because this is cohomology of O of -1. And there are two-dimensional, well, two morphisms, if you wish, a two-dimensional space of morphisms from O to O of 1. In other words, this is the algebra of the path algebra of the quiver with two vertices and two arrows. This is a very well-known algebra. This is called the Kronecker quiver with two arrows, but in general, you can have more. And then suddenly, now representation. So what is this? This becomes representations of quivers. And people love representations of quivers. Representation of quivers is is simply like very advanced linear algebra, but you can do plenty and plenty of stuff there. Similarly for finite dimensional algebras. So the same happens for other varieties. It turns out that you can find, so the keywords here are exceptional collections. And the immediate outcome from this, which was very, very important for theoretical physics, outcome, these are instanton bundles. Progress with instanton bundles, namely when you see here something like Beilinson monad, and usually instanton bundles are defined over P2, while instanton monad is exactly the result which comes from Beilinson's theorem. But also, if you want to generalize instantons to other varieties, which physicists seem to enjoy, not very much, but still, this is what's used. Well, let me just say the last things because I cannot dive too deeply in the last 5 minutes. So the next, starting from, so this was an explosion, the result of Beilinson, and actually a fascinating theorem by Bundle-Orlov says that if omega x, this dualizing bundle, the determinant, the top differential forms of your smooth projective varieties, if it is either ample or omega x inverse is ample, well, or so I said either, or anti-ample. So again, x is smooth projective. I'm not repeating this. For instance, if you take a high enough power and it gives you an embedding in the projective space, and this often happens, if it's either ample or anti-ample, then actually d of x is a complete invariant of x, meaning that if two varieties have, one of them is of such form and you have an equivalence of derived categories, well, I should explain what it is, it should preserve some structure, then the two varieties are isomorphic. So out of this came even more interest, because on the one hand, for some varieties, you get this equivalence, but for some other, so more generally, for instance, if x is a Calabi-Yau, so omega x is isomorphic to O of x, then there exist varieties with equivalent derived categories. So there exists non-isomorphic. And this leads you to a very large discussion that again comes out of physics, but has arrived into mathematics. And this is, I will write in parentheses, homological mirror symmetry. So the formulation of mirror symmetry by Kontsevich essentially uses as its input equivalences, as its output, sorry, equivalences of certain categories, where on one hand side you have derived categories of coherent sheaves, and on the other you have Fukaya or Fukaya's idle categories. So again, it's an essential part of discussion, which is very, very conjectural, of course, but at least these are some of the directions where you can slowly go from here. All right, I think I'm more or less out of time, so it's a good place to stop. Thank you.